This talk I'd like to dedicate to Inge Lehmann. Here's a picture of her. Lived 1888 to 1993. So, see, I was 9 years old when she passed away. She lived to be 104 years old too, which is really crazy. My drawing is a lot worse than this one, but you'll see you have your silicate mantle, your solid inner core, and your fluid outer core. The solid inner core is what we're going to go over, and this has to do with determining how long it took for the Earth to form. Here's my picture. So, black and white. So you have the whole Earth, and you have the mantle. You have the liquid outer core, and you have the solid inner core. That's that. Now, to actually understand how large of an object we're dealing with here, the only real way to kind of comprehend it is to do a math equation for volume. Now, the math equation for volume is volume equals 4/3 pi r cubed. And that's right up here, it's equation. So you have pi, which is I believe that's circumference as opposed to the diameter. And you have the radius cubed. So you take this measurement, cube that, multiply it by pi and 4/3, and I did that at the bottom here, which comes out to 7.61 billion cubic kilometers of iron nickel alloy. Now, I don't know if you guys are familiar with heavy duty machinery like forklifts, cranes, earth movers, stuff like that. But the back half of those things is ballast. So, when they lift heavy things up over here, the ballast keeps the machine from flipping over, and it can lift really heavy things because the ballast keeps it balanced. And on the forklift I have here at work, the ballast I think weighs around 3,000 pounds. But it doesn't look like much. You see this giant iron brick at the back end of the forklift. It doesn't look like much. But take that and understand how heavy that is, and how much force that thing can impart when you lift something up on the fork end. And then really try to conceptualize how much volume is 7.6 billion cubic kilometers of iron nickel alloy. We're not talking about a little pebble. We're not talking about Carl Sagan's pale blue dot here. This is an incredibly vast structure. It's a tiny bit smaller than the moon in complete volume. But it's solid iron nickel alloy. It's insane. And the reason why I wanted to go over this is, now, depending on how fast that object forms inside the interior of a star, I have it sort of like as a pearl. Okay, so in a very young star, they don't have any cores, but eventually the iron finds the center in the interior of the star, and that iron and nickel starts to deposit and deposit and deposit and deposit and deposit, and it grows like a pearl in concentric layers. Now, they're not layers per se, exacting like tree rings, but they do, the core does layer itself over time spherically. And that's important because if it layers spherically from the inside out, then depending on how fast that thickness is increases, you can determine how long it took that structure to form. Now, with tree rings, it's different because you have the winter summer cycles when the tree grows faster in the summer, and then it grows slower in the winter. And those repeated cycles give the appearance of rings. So when you slice a tree in half, you see the rings and the growth patterns, but those aren't actually, those are just the growth cycles, and you can tell how many years old it is. With the iron nickel core, I think it's going to be a challenge to figure out how fast iron and nickel deposits. But if you can do that, you can set a lower age limit on how old objects are in the solar system. Now, I arbitrarily set core deposition as 1 meter of material every 8,200 years. So if you have iron just arbitrarily sitting there, like imagine a star, and it has a little bit of the substrate there, you'll have a thickness in radius of 1 meter out from the very, very center of that star, taking about 8,200 years to form. Now, that's through very, very slow vapor deposition. And think about like stalactites and stalagmites inside of caves. You know, you have the calcium carbonate when it, drips, and it forms the, I think it's calcium carbonate, I'm not too sure, but it drips. And over time, that water brings all that material and it forms the stalactites and stalagmites, and then they sometimes can connect all the way to the center. That's similar to the interior of a star, where you have the iron. Well, for one thing, it's really freaking hot. So even if you were to have something to form, it'd still have to be considerably cooler. That way, that iron and nickel will, clump together. It won't still be ionized, and it won't even know that it's there. But it also takes a star cooling down over a very long period of time, so that that iron can clump together in the center of the star. And I figure 8,200 years to completely, crystallize is reasonable per meter. And that's per meter thickness for the entire core. It isn't just one little spot. It's the entire thing per meter, 8,200 years. And that being said, Earth has a lower age limit just to form the core of around 10 billion years. And that is the original number that I had thought up of when I was doing the Walensky-Taylor diagram. I set Earth to be about 10 billion years old, because that's basically the very first, the core is the very first structure that forms inside the star as it evolves. And then it layers on the mantle, and then the crust solidifies in the very outer regions. So the crust, mountain ranges and, all the basalt and the ocean basins, that material is the last material to form inside the star, because it's the outermost material. It's just the law of superposition. The higher material is the youngest, and as you go lower and lower and lower, it gets older and older and older, which means the core is the oldest object on the Earth. Of course, you're not going to read that anywhere in geology textbooks. I don't know why. But the core is very old. So you take the core first, the oldest structure, you date that, and then you work backwards from that. And I think that's sound reasoning. For Mars and Mercury, their inner core is a bit larger than the Earth, at around 1.8 million meters. And that sets it at about 14.7 billion years lower age limit. So that being said, Mars and Mercury are most definitely older than the Earth by at least 4.5 billion years. So the age of the solar system itself are older than the Earth. And that's a lower age limit, meaning they're probably vastly older. We're just talking about the core here. The moon, 1.3 billion years, lower age limit, right there. Of course, there are lots of variables to add. There's Io, there's Ganymede, and then Callisto I have as impact remains. I think that's the remains of an impact, because it's undifferentiated for the most part. It doesn't have a differentiated core. And then I got Pluto, that's a guess. Venus, that's a guess. Titan, that's also a guess. But you'll see there that I set a lower age limit for these objects in terms of how fast the core might deposit as the star evolves. And just to review, look at the Earth, look at stars as being like giant oysters, if you will, or mollusks. And you have the substrate enter into the mollusk, and it's like, oh crap, we don't want this little piece of irritant in here, so cover it up and try to make it to where it doesn't harm the fleshy regions of the oyster. and to protect the oyster protecting itself. It's kind of like what stars do is that when a large asteroid, I don't say the star's trying to protect itself, that's kind of weird, but imagine the asteroid entering into the star and it being big enough to where, hey, the star isn't going to destroy it, and it's a huge, huge mass, and it moves and it falls all the way to the center of the sun because it's a giant plasma ball, and then that acts as the substrate, which then the iron that's in the surrounding regions will find, and then start layering on top of that, building the core inside out. And that's the first object that forms when you form a planet. So all in all, core accretion happens inside the star, and it's very different than what establishment says, because they have iron clumping together in the vacuum, and there's nothing there to provide direction for any kind of material to layer onto that substrate in the vacuum. It's like, how exactly do dust clouds just know where to clump together? It's very strange reasoning. You would need something really hot, really big, really have a large gravitational field so it can grab objects from outer space as it's moving through outer space, and then it layers that material like a pearl in the center, and as it continues layering that substrate, the outer atmosphere starts dissipating too. So that's basically it. And it would be so awesome if Inge Lehmann would have known that she had discovered the core of an ancient star. Put Jules Verne to shame. All right, you guys, later.